This video is for the next QOD, and it is mostly related to ions. The first little bit is just going to be going over some common ions that you should know. And then the next is going to be how to name oxyanions. And then finally, we're going to talk about, once we know how to name oxyanions, how to name oxoacids. And so let's talk first just briefly about names and formulas of common ions. Just about all of these are things that we have already done in class. But I'm going to hand out a sheet that has these ions on it, and these are really the ones where I do expect you to be able to correlate name with formula. So if you look at the monatomic cations, I've got them arranged by charge. Hydrogen, lithium, sodium, potassium, rubidium, cesium. These are the group 1 elements that we already know ionize to give you a +1 charge. So there's nothing new about these. Silver, which is a transition metal. Also, although many transition metals ionize to give you more than 1 charge, silver only gives you a +1. And so you notice it doesn't have a Roman numeral there. But you should memorize silver as +1. It comes up a lot in lab things and in solubility issues, so you really need to know that. And then copper, the two transition metals of variable charge that I really want you to have memorized, their charges are copper and iron. And so copper gives you a +1 and a +2, so you need to know that that copper comes up as a +1. So copper 1 has a charge of +1. If we go on to number 2, again, here's all the group 2, magnesium, calcium, strontium, barium. Zinc, which appears in the periodic table to be a transition metal, actually doesn't behave like a transition metal, and it only oxidizes to give a +2 cation. And so we do not write zinc with Roman numeral 2, it's just zinc. So you need to know that zinc is +2. Here's now the other ion of copper. So there's copper 1, there's copper 2. Lead is one that we haven't talked about before, lead 2, but lead can give you a +2 and a +4. I'm not really concerned that you know about lead 4 because it really doesn't come up in this class, but lead 2 will come up a lot, and so you should be familiar with lead 2. Iron is the other transition metal that I need you to know both of its oxidation states. There's iron 2 and there's iron 3, so I've got iron 2 here under the +2 cations, and then there's aluminum as a +3, which we've talked about, and then iron 3 to complement iron 2. In the monatomic anions, these are all the main group nonmetals that we've been over before, but I've added one more, and that is hydride, because hydrogen can ionize 2 ways. It can both lose its electron to form the hydrogen ion, which we've talked about previously, but it can also gain an electron to form the hydride anion, and so you should be familiar with hydride as well. The polyatomic ions, they really are just the 10 that we've talked about before, but I've added one more, and that's the hydronium ion. This is important when we get into acid-base chemistry because the hydronium ion is what you get when you add the hydrogen ion to water. And so that's one more thing. So the new things that are here that we haven't talked about up to now would be hydronium, hydride, silver, zinc, and lead 2. We had previously talked about copper 1 and copper 2, and we had previously talked about iron 2 and iron 3. Okay, we're going to switch over now and talk about naming oxyanions. And so oxyanions are just really defined as anions that have a central atom, nitrogen or chlorine or carbon or sulfur or phosphorus, surrounded by some number of oxygens and then a fixed charge. And we've talked about before that polyatomic ions are really sort of charged molecules. And so this is essentially, you can think about it as a molecule NO3 that's got a charge of -1. So these 4 atoms are always going to travel together. They can't be pulled apart, and the whole thing has a charge of -1. And these are among the 10 that you had to memorize for me. There's a little sort of scheme you can learn to remember what their formulas are. This comes right out of your textbook. But if you line these up by period and by group number, what you'll find is that the oxyanions that are from period 2 can have only a maximum of 3 oxygens, and so carbonate has 3 and nitrate has 3. If you get into period 3 or below period 4, you can have a maximum of 4 oxygens. So because phosphorus, sulfur, and chlorine are in period 3, then phosphate, sulfate, and perchlorate each has the maximum number of oxygens for period 3, which would be 4 oxygens. So things in period 2 can have up to 3 oxygens. Things in period 3 can have up to 4 oxygens. And then once you've sort of arranged them this way, the other thing that this points out is if you start on the right, at the far right, that's got a charge of -1. Then as you move left, it's a charge of -2. If you move left again, it's a charge of -3. If you go up in period 2, it starts with nitrogen, nitrate, so -1, and as you go left, -2. There's obviously no oxyanion of oxygen. That wouldn't make any sense. And as it turns out, there's no oxyanion of fluorine either. Okay, so that's 5 that you know the names and formulas of. From those 5, well, I guess what I would say is, but there are lots and lots of different oxyanions. I'm just going to give you a bunch of examples here. ClO2 minus, BrO4 minus, NO2 minus, SO3 minus 2, PO2 minus 3, SeO4 minus 2, ASO3 minus 3. You've never seen any of these. They're not on the list of these 5 or any of the 10 polyatomic ions you've had to memorize up to now. But it turns out that if you can learn some simple rules, it's not difficult to name any of these 7 other things I've got here, or indeed to name a lot of other oxyanions I could give you as well. So let's talk about those rules. The first thing is there are 4 prefix and suffix combinations that you want to learn when it comes to naming oxyanions, and these have to do with how many oxygens are attached to the central atom. If it has the maximum possible number of oxygens, it is per blank 8, and I'm going to tell you what I mean in just a second by the blank. 1 fewer oxygen would be blank 8, and then ite, and then hypoite. This may seem a little confusing right now, but when I actually put it into practice, you'll see what I'm talking about. And what this is that there are increasing number of oxygen atoms in the oxyanion. So something that ended in ite would have 1 more oxygen than something that was hypoite. Something that was ended in 8 would have 1 more oxygen than the ite, and something that was per 8 would have 1 more oxygen than the 8. So again, this sounds kind of weird. What's an example? Well, your book, again, this is from the book, gives you the example with chlorine. So the thing in the blank, because we're talking about chlorine, would be chlor. And so the chlorine oxo anion that's got the most oxygens, ClO4 minus, is perchlorate. You take one away, you get chlorate. Take another one away, you get chlorite. You take another one away, you get hypochlorite. The oxyanions of the halogens are the only cases in which you actually have all 4 possibilities. For other central atoms, you don't have all 4, per 8, ite, and hypoite. But for the oxyanions of the halogens, you do. So the halogens are kind of a good template to learn this on. So you know perchlorate, you had to memorize it. Therefore, from this, you can work out that if it has 1 fewer oxygen, ClO3, it would be chlorate. 2 fewer oxygens, ClO2 minus chlorite. 3 fewer oxygens, ClO minus hypochlorite. So given that, let's think about how we might name some other ones. So what we know already and what we've learned is phosphate, which is PO4 3 minus. So what would we call the anion that is PO3 3 minus? By the way, any point along the way in this video that you want to just stop the video while I'm asking you these questions and think about what the answer might be, you can go ahead and do that. So PO3 3 minus, because it has 1 less oxygen than phosphate, that's going to be called phosphite, because ite is 1 less oxygen than 8. Okay, how about NO2 minus. Well, you know NO3 minus is nitrate, and therefore NO2 minus is going to be nitrite. How about SO3 2 minus? Well, we've learned that SO4 2 minus is sulfate, and so SO3 2 minus is going to be sulfite. One thing that's really important that I want you to notice here, the charge, when you add or remove oxygens, it changes the identity of the oxyanion and it changes its name. But within a particular central atom, the charge always remains the same. So whether it's PO2 or PO3 or PO4, because that central atom is phosphorus, and you know that for phosphate it's -3, they're all -3. Because you know that nitrate is -1, you can assume incorrectly that nitrite is also -1. And because you know that sulfate is -2, you can assume, again correctly, that sulfite is also going to be -2. Charges don't change. They're fixed by the identity of the central atom. Okay, so that's the first thing, to go through that whole list of the per-8 and then the 8 and then the ite and then the hypoite. The other thing that is important to know in naming oxyanions is that central elements in the same group behave the same way. They're named the same, they have the same charges, with one exception, and that is that nitrogen in group 5 does not follow the pattern of phosphoric or arsenic, which are also in group 5. Otherwise, any other instances of oxoanions, it is always simply going to follow the pattern of other elements in the same group. And so just to say, nitrogen and phosphorus do not behave the same way, but phosphorus and arsenic behave the same way. Sulfur and selenium behave the same way. Chlorine, bromine, and iodine all behave the same as each other. And again, there are no oxoanions of fluorine for reasons that we may get into later in the course or may not. I couldn't really say. All right, so elements in the same group behave the same way. Therefore, what would be the formula for bromate? Well, and so again, if you want, you can pause this and think about it and then turn it back on. I'll go ahead and describe how you would sort of reasonably get to the answer. Well, the central atom here is going to be bromine. Bromine is in the same group as chlorine. We know the chlorine one that we had to memorize was perchlorate, ClO4 minus. Therefore, we can assume that perbromate would be BrO4 minus. And so if we take off the per, and just to get to bromate, that means we had to take one oxygen off. Therefore, bromate should be BrO3 minus. And that's correct. Because all oxyanions of chlorine have a charge of -1, we can assume that all oxyanions of bromine have a charge of -1. Because we know from chlorine that in the halogens, if it's got 4 oxygens, it's per. Then bromate is 1 less oxygen than the per. If the per is 4, then the 8 is simply, simple 8 is going to be 3. Bromate is BrO3 minus. Selenate. Selenium is in group 6, and it's the same as sulfur. And we know that sulfate is SO4 minus 2. Because things in the same group behave the same way, we can assume that selenate is going to be SeO4 minus 2. Arsenate. Once again, we're looking at something that we haven't learned, but arsenic is in group 5, the same as phosphorus. So we can assume that arsenic is going to behave in terms of name, charge, and number of oxygens, the same as phosphorus. Because phosphate is PO4 3 minus, we can correctly assume that arsenate is going to be ASO4 3 minus. So let's go back to the 7 that looked so daunting a few minutes ago and see if we can name them now. ClO2 minus 1. Well, perchlorate is ClO4. If we step down to ClO3, that would just be chlorate. And if we step down to ClO2, that is going to be chlorite. Notice again that the magnitude of the charge doesn't change because all the halogen oxyanions have a charge of -1. BrO4 minus, because ClO4 minus is perchlorate, then we can correctly guess that BrO4 minus is going to be perbromate. NO2 minus, we've already looked at this one. NO3 minus is nitrate, therefore NO2 minus is nitrite. SO3 2 minus, we've also looked at that one because SO4 2 minus is sulfate. We can guess that SO3 2 minus is sulfite. PO2 3 minus. PO4 3 minus would be phosphate. Therefore, PO3 3 minus would be phosphite. Therefore, PO2 3 minus would be hypophosphite. SeO4 2 minus, we looked at this on the previous slide because selenium's in the same group as sulfur. SO4 2 minus is sulfate, therefore SeO4 2 minus is selenate. And then here's one where you have to make two switches. Arsenic is in the same group as phosphorus. Arsenate would be ASO4 3 minus, therefore ASO3 3 minus is going to be arsenite. Well, the last thing we want to talk about is the concept of converting oxyanions to their parent acids. And what that really means is that oxyanions come from what are called oxoacids. Now, an acid, as we will learn in a subsequent chapter, is a substance that can donate or create H+ ions. And so if we have an oxyanion and we're trying to convert it to its parent acid, we are going to add an H+ for each negative charge on the oxyanion until we have a neutral compound. What does that mean? Well, let's take a look at three oxyanions that we know well: nitrate, sulfate, and phosphate. You'll notice that nitrate has a charge of -1, sulfate has a charge of -2, phosphate has a charge of -3. So to get to a neutral compound from nitrate, we only add one H+. A plus plus a minus cancels out, and now I've got a neutral compound. And so the formula for the parent acid of nitrate is going to be HNO3. Because sulfate has a charge of -2, I have to add two hydrogens to get to a neutral compound there. And so the formula of the acid that sulfate comes from is going to be H2SO4, because I need to add two hydrogens to cancel out the 2- charge. Because phosphate has a charge of -3, I'm going to have to add three hydrogens, and therefore the formula for phosphate's acid is H3PO4. And so you can do this for any oxyanion. Just take a look at the magnitude of the negative charge, add that many hydrogens, and they always go on the front of the formula, and you've got your acid. Now we need to know how to name these acids. So we need to know how to construct them based on the formula of the oxyanion. Now we need to know how to name them. And I did not come up with this mnemonic, but it seems to work well. One of my students at UNC did, but it seems to work out pretty well. And that is this phrase: I ate the ick and I got the itis. Okay, I ate the ick and I got the itis. Well, what does that mean? Well, if I am taking an oxyanion and changing its name to correspond to the acid that it came from, if it ends in ate, then that becomes ick acid. That's I ate the ick. If it ends in ite, then it's going to become us acid. That's the itis. And then the prefixes hypo and per will simply carry over if they're there. So that's kind of hard stomach or to digest what I'm saying here, but let's actually just do some examples and hopefully you understand how this works. HClO4, HClO3, HClO2, HClO. It works well to use the halogens and the oxyanions of chlorine to do this because, as I said before, the halogens wind up having all four possible naming combinations. HClO4, what oxyanion did it come from? It came from ClO4 minus. This is called perchloric acid because 8 goes to ic, acid. So perchlorate goes to perchloric acid. HClO3 came from the chlorate anion, therefore it is chloric acid. 8 goes to ic. This is chlorous acid, HClO2. I'm sorry, this is HClO2 minus is the chlorite anion, therefore it becomes chlorous acid, ite to us. I ate the ick and I got the itis. And then the hypochlorite anion would become, its complementary acid is hypochlorous acid. Well, let's finish up. We're just about done here, so I'm going to finish you up with some examples. What would be the formula for selenous acid? Us comes from ite. So selenous acid would come from selenite. And then you would work out the fact that selenite is SeO3 2 minus because selenate is SeO4 2 minus. If selenite is SeO3 2 minus, selenous acid is going to be H2SeO3. What is the name of the acid HBRO? Well, that is going to come from the oxyanion BRO minus. Remember, in the halogens, the one with 4 oxygens is per 8, 3 oxygens is 8, 2 oxygens is ite, 1 oxygen is hypoite. So the oxyanion that this comes from is hypobromite. Therefore, this is hypobromous acid. There will be problems for you to look at from the book to think these through, and then the QOD will be on this topic tomorrow. Thanks so much.